Today, we're going to tackle a really classic system design problem. How in the world do you generate millions, even billions of unique IDs across servers all over the globe without ever having two of them be the same? Let's dive in.
Think about it for a second. Every single time you post something, buy something, or sign up for a new service, you're creating a new piece of data. And in this just massive ocean of information, every single one of those actions needs its own unique identity to keep the whole system from descending into total chaos.
And yeah, look at these. They aren't simple little numbers like 1, 2, or 3. They're these huge, kind of random-looking numbers that are basically the lifeblood of these massive systems. So, the big question is, how are they made without ever creating a duplicate?
So, if you've ever played around with a single database, you've probably used a feature called auto-increment. It's super simple, right? The first thing you add gets ID 1, the next is 2, and so on. Easy. But what happens when your app gets so popular that you need more than one server? Well, that's when this simple, elegant solution completely falls apart.
This is really the heart of the problem. We are talking about some serious scale here. Imagine two different servers, maybe one in New York and one in Tokyo, both trying to create ID number 5834 at the exact same millisecond. Bam, you've got a collision, you've got data corruption, you've got chaos. Our goal is to design a system that can handle over 10,000 of these requests every single second and never fail.
Okay, so before we can even start looking for the right answer, we have to define the question properly. We need a clear checklist. What does the perfect ID even look like for our system?
And here it is, our wish list. First, it absolutely must be unique. That's the whole point, right? Non-negotiable. Second, we want numerical values only, because numbers are just way faster for databases to work with. Third, it has to fit into a neat 64-bit package, which is a really standard and efficient size. Now, here's a tricky one. It has to be ordered by date. This is super important for being able to sort things chronologically. And finally, it's got to be fast. Like, really fast. Over 10,000 IDs per second fast.
With our checklist in hand, it's time to put some of the most common solutions to the test. We're going to run them through what I like to call the gauntlet, and see which ones, if any, actually make it out alive. Our first contender is a pretty clever trick. It's an attempt to make that old auto-increment idea work across more than one database. It's called multi-master replication.
The way this works is actually pretty smart. Instead of having every server count up by 1, you give each of them a different starting point and a different step. So with 2 servers, you could have server 1 only generate odd numbers, 1, 3, 5, and so on. And server 2 only generates the evens, 2, 4, 6. Hey, no collisions. Seems pretty clever at first glance.
But here's where it fails our checklist. It's a real headache to scale, especially across different data centers. And crucially, the IDs are not time sortable. An ID like 6 from the second server could be created after an ID like 7 from the first server. That makes sorting by time impossible. It's just too fragile for a big system. So, down it goes.
All right, next up to the plate is something you have definitely seen all over the web, the UUID, or Universally Unique Identifier.
Now, the beautiful thing about UUIDs is that there's no central coordination needed. Every server can just mint its own ID whenever it wants. The number itself is so massive and so random that the probability of 2 servers ever creating the same one is it's astronomically small. We're talking you'd have to generate 1 billion of these every second for 100 years to even have a 50% chance of a single collision.
So while UUIDs are amazing at preventing collisions, they fail our checklist, and they fail spectacularly. They're 128 bits, which is double our size limit. They're totally random, which means you can't sort them by time. And for a database, that's a performance nightmare. And to top it all off, they often contain letters, so they're not even purely numeric. Another contender bites the dust.
Okay, our third contender takes the complete opposite approach. Instead of every server for itself, what if we had one single, authoritative source for all our IDs? This is the ticket server model, which was made famous by Flickr.
The idea here is really simple. It's kind of like taking a number at the deli counter. Whenever a web server needs a new ID, it just asks this central ticket server. The ticket server just hands out the next number in line, guaranteeing that every ID is unique and perfectly sortable.
And you know what? This gets us so much closer. The IDs are numeric, they're sortable, it actually works. But, and this is a huge but, it introduces a brand new, terrifying problem. a single point of failure. If that one ticket server goes down, your entire application grinds to a halt. No new users, no new posts, no new orders, nothing. For any large-scale system, that is just an unacceptable risk.
So all of our contenders have failed the gauntlet. We need something that's distributed like a UUID, but also ordered and numeric like a ticket server. This is where a truly brilliant solution comes into play, one developed at Twitter called Snowflake. And the whole philosophy behind it is divide and conquer. Instead of trying to treat the ID as one single giant mysterious number, Snowflake builds it from several smaller, much smarter components. Each one has a very specific job to do.
And this, right here, this is the secret sauce. This is the genius of the whole concept. A 64-bit Snowflake ID isn't just one number. It's a composite, a little package made up of 4 different sections. So let's break down how each part works together to build our perfect ID. The first and biggest part is a 41-bit timestamp. Now, this isn't a random number. It's the number of milliseconds that have passed since a specific start date, and just like that, it solves our sortable by date requirement. The natural flow of time itself guarantees that new IDs are always bigger than old ones, and those 41 bits give us enough runway for about 69 years worth of IDs. Okay, so we've got time covered, but what about the distributed problem with all those different servers? Well, that's what these next 2 sections are for. A 5-bit data center ID and a 5-bit machine ID. This setup means you can have 32 unique data centers, and inside each one, 32 unique machines. The ID's origin is literally baked right into the number itself, so 2 different machines can never create the same ID even in the exact same millisecond.
But you might be wondering, what if one really fast machine needs to create multiple IDs in the same millisecond? That's where these final 12 bits come in. It's a tiny sequence number, a little counter that ticks up for each ID created within that millisecond, and then it just resets to 0 at the start of the next one. With 12 bits, we can generate over 4,000 unique IDs per machine per millisecond, which absolutely crushes our requirement of 10,000 per second.
And this part is just so cool. It proves the whole concept works. You can take any Snowflake ID, pull out those 41 bits, do a little bit of math, and get back the exact date and time it was created, right down to the millisecond. It's this beautiful, elegant fusion of time and location data, all packed into a single, sortable 64-bit number.
Now, as elegant as a design like Snowflake is, there are always a few real-world details you have to consider before you just drop it into production. First, since the whole system relies on accurate timestamps, keeping your server clock synchronized is absolutely essential. You'll need something like the network time protocol. You can also tune the bit lengths. If you don't need 32 data centers, but you want the system to last for 100 years, you can borrow some bits from the data center ID and give them to the timestamp. And finally, you have to remember, this ID generation service is mission critical. It has to be highly available. So there you have it. From a simple counter that breaks at scale all the way to Twitter's Snowflake, we found a robust, elegant way to generate unique, sortable IDs for a massive distributed system. It's one of those foundational pieces of tech that really powers the modern internet. The only question left is, now that you can generate a unique ID for pretty much every grain of sand on Earth, what will you build?